Okay, so welcome to the seventh week of the live tutorial session for the course Points and Topology, and today we'll be discussing this compactness and countability of a topological space. So mostly as the assignment 8 problems deals with mostly compactness, so like most of the problems are based on compactness, and one problem we'll discuss about the countability. So the first is in the matrix, if X is a metric space, then and a subspace of X is compact, then in a metric space it is always closed and bounded. So I'm saying that in general topological space it is not true. So in particular the boundedness, you can't say the boundedness, but at least closeness we can say. So so this question asks that give an example of a topological space where a subspace is compact but it is not closed. So anyone have any example? Okay, so first of all, as like you should start with the a topological space which is not metrizable kind of. So can you think of some topological space which does not comes from any metric? We have discussed that previously also, that it cannot come from any metric. So can you think of some topological space?
Sierpinski space.
Okay, but they are like okay, that then can you say what is the subspace and what is the set where the subspace is compact? Sierpinski, I actually didn't discuss, but yes, sure, that is not metrizable, you can say. So the example I have in mind, so take real number with co-finite topology. So R with co-finite topology. So these also we have like discussed previously, and see that this cannot be metrizable. So we basically say the countability or some countable dense subset about that thing. So in matrix space you always have a countable countable dense subset, but in here like, so okay, cofinite topology there are also okay, we probably have discussed second countability. So R with cofinite topology, that is not second countable, so that means you can't have any countable base for this topology. But in a metric space you actually, in R you actually have a second countable, like on R if you have metric, then actually that gives you a countable basis. Okay, so this is not actually a topological space, so as we are dealing with this question particularly. So but here if you in particular take natural number as your set A, then A is an infinite set, and this is, I'm saying, this is also compact. Okay, so can you see why this is compact? So to show this is compact, you start with any cover of n. Okay, so is let's say union over ai for a is open in R, then by the cofinite topology we know these are open, so their complements has to be finite. Then it's particular, let's take a so then ai complement are finite sets in R, okay, by the definition of openness in this topology. So just fix one thing, and ai complement, so now a intersection, this implies a intersection ai complement is finite, right, for any I. So how many points are there outside of this ai set? So only finitely many terms of a can be there outside of this ai, okay, for each I. So fix one, so any fix I naught, let's say I'm fixing I naught, there are only finitely many points of a lies outside of ai naught, okay. So say a1 a2 up to ak, okay. So take aij for aj belongs to aij, okay. Then clearly then a is contained inside this ai naught and union over this all aij, okay. So j equal to this union and j equal to 1 to k aij, because only except this point everything else lies in this ai naught. So if I like take the sets which also contains this a1 through ak, then whole of your a lies inside this union, right? And this is a finite collection of your given collection, like given cover. So this is a finite sub collection. So this implies a has a finite subcover. So this is compact, but this cannot be closed because this is an infinite set. Then it cannot be closed, right? So can you just like, if it is closed, then its complement has to be open, and a set is open in this if its complement is finite, right? But this n is like not finite, so it cannot be closed as equal to n is infinite, so A is not closed. Okay, so this is an like example where this topological space is not metrizable. Like this is an one like also reason why R with cofinite topology cannot be metrizable, because in metric space if you have a compact set that has to have closed, but in this case you have a compact set which is not closed, so the topology cannot comes from any metric. So that is also a reason for non-metrizability of this space. Okay, clear? Okay, so let's go to the next problem then. So here again, like related to this closed boundedness of a compact set. So in metric space you have seen that a compact space is closed and bounded. So here I'm asking the like converse thing, as it happens in Euclidean space that every compact space is closed and bounded, and any closed bounded sets are compact. So does it happens in any other in general metric space? So in general metric space HT, if you have a closed bounded set, does it necessarily mean that set is compact?
No.
Any example?
Yes. We can take an infinite set and we can take discrete metric over that.
Yeah, exactly. So we can take let's say infinite set. So let's take R with the discrete metric. So HD equal to R with okay, just let's take D, where D is discrete. Then like any set is if you take any set that is closed and that is also bounded because the metric itself bounded. Like if you consider any ball of radius 2 around any point, let's say 0, then it is all of R, because your metric is either takes value either 0 or 1. So if I just write by definition, this is consist of all x belongs to R such that dx comma 0 is less than 2, but the metric itself is either 0 or 1, so it takes all possible value, so it is like x belongs to R only, and this restriction is not a restriction at all, so this is all of R. That means R is itself bounded, so any subset of this is also bounded, and any subset of its by definition, like from the metric also, it is closed as well as bounded. So but any infinite set cannot be compact, right? So again, let's take the n natural number set. So this you can write as union of, like if you consider this as a cover, so let's say n belongs to n, like union of the singleton sets. Each of them any subset is open, so the singleton sets are also open, so is an open cover for n, but So BDDB is for boundedness. Okay, bounded. Okay, open cover for n, but because all the sets are disjoint, so if it is has finite subcover, then n has like finitely many elements, but n has infinitely many elements, so that cannot happen. So but it can't have a cover as n is infinite. Okay, so this is an example of such cases, that is compact. Although it is closed and bounded. Okay, so the converse of the closed boundedness thing is also not true in any arbitrary metric space. Okay, so next thing, so again consider the closed interval 0 1. So closed interval 0 1, this is in usual metric, in the usual metric of R, it is closed and bounded, so it is compact. So we ask the same thing in co-countable topology, whether this is compact or not. So any guesses at least whether it is compact or not?
Any open set with any open set in co-countable topology will have uncountable number of elements.
Sure.
So if we'll follow that same thing as we followed for natural numbers, so if I make an open cover of closed interval 0 to 1,
Sure.
then only countable many elements will lie outside any particular set from the open cover.
No, that you can't say. Like if you delete some like the open sets are surely uncountable, but if you delete uncountable many elements from an uncountable set, that like need not be always countable. That you can't say anything.
Okay, yes. Then it's not compact.
Okay, then
No, I'm asking, then it's not compact.
yeah, it is not compact. So then can you produce a cover which cannot have a finite subcover?
Then I'll take some open balls with center at irrational number or something.
No, here balls does not make sense because this is not metric space.
Ball means open interval containing.
Open interval containing, but that is not open, right?
Because its complement is not.
Yes, not finite. So think of some countable set, and then you probably take the complement and like that as cover. in 0 1, can you think of like simple something simple
Rational number, all the rational numbers.
Yeah, rational number you can take, but the rational number there you have to like you can take a like enumeration of that thing, and that is also possible surely. So for
Or
example,
we can take one by n.
exactly,
Like,
so 1 by n is also countable. That is a like more concrete choice because you want to get something like something deleted by these things. So idea is basically consider AI as just it start from 1 by I. Okay, so consider 1 by n such that n is greater equal to I, all the numbers. So it start with 1 by I, 1 by I plus 1, and so on. Okay, so for I equal to 1 to up to infinity. So now you consider the complement of this thing. Each of these are countable. AIs are countable, so this implies AI is complement. These are open in 0 1 with this co-countable topology. Now so, and this 0 1, this is also union. You can write this as union of this AI's complement, right? Because like what is the complement? So in the A1 it is like consist of all numbers of 0 1 except this 1 by n, like 1 by 1, 1 half, 1/3, 1/4, and so on. So in second, so the 1 included, right, because it start with half, so 1 is there. In the second thing it start with sorry, in third it start with 1/3, so half is there in the complement, right? So as 1 by n, this is belongs to actually a, so what is happening, 1 belongs to A2 complement, right, because 1 is there. So 1 by n, so it is belongs to a n plus 1 complement, for each n belongs to n, right? So in the A1 the only sets that is not there in like points that is not there are 1 by n thing, but 1 by n belongs to like n plus 1 complement. So all of these things are there, and this is the complement. So this complement is not in R, but this is closed 0 1 minus AI. Okay, so these sets clearly cover this 0 1 whole 0 1. But can there be any finite collection that covers also this? Like one thing is here also, you can observe that these sets are actually nested. So A1 is like biggest one, then A2 is subset of that thing because you are deleting one point from there, A3, and so on. So the complements of them are also nested. So A1 complement is subset of A2 complement, A3 complement, and so on. Okay, now if you have a finite collection of these sets, so for a finite collection, A I1 complement up to a ik complement, union will be the maximum of them, right? The union of a ij complement for j equal to 1 to k, this will be AP or p equal to, because this is inclusive, so the maximal index will contain all the others, so p is maximum of I1 through Ik. Okay, and this AP complement, sorry, so this AP complement does not contains the element after 1 by p, right? 1 by p, 1 by p plus 1, those points are not contained there. Any finite collection, this is that, and 1 by n does not belongs to AP complement for any n greater equal to p, right? So this implies so 0 1 is can't be covered by finite subcollection so obviously this is a open cover, okay, by finite subcollection of these AI complements. So that is 0 1 can't be compact. So 0 1 with co-countable topology, it is not compact. Okay, fine. Like it is separate from the cofinite thing. In the cofinite thing, in the first question we just have seen that any infinite set is compact in cofinite topology, because the co-countability is not there, so finiteness will guarantee that outside of any open set there are only finitely many elements. So if you consider those elements in some of these cover set, then you will get definitely a finite subcollection from the set. But in this case, as your collection can be infinite, so you can't cover the whole set by in general you can't cover that by finite subcollection. Okay, so 0 1 in cofinite topology is compact but not in co-countable topology. Okay, so let's go to the next problem then. So here again this is basically related to one of the assignment problem. So like there is if you recall, there are thing that compact subset with locally connected and compact subset whether it has finitely many components or not. So I just delete the locally connected thing and ask the same thing, that whether every compact subset in a metric space has finitely many components or not. Okay, so metric space is also extra assumption in this case. So do you think this is true or false? Like if you have any example in mind. Any guesses, true or false? Like blind guesses at least.
So when we say components, what does it mean? Component means like as they were in the connected space.
Yes, the maximal connected subset in that space. Like
Okay, so now
yes. Like there cannot be any connected subset in between that contains that component. So component is the maximal possible connected subset there. So there cannot be like there may be different components. So number, yes.
I think then they have to be finite.
Why?
Not sure, but if because in metric space, if we have a compact subset, then it has to be bounded.
Closed and bounded, sure.
Closed and so if component mean the maximal connected set. So not sure.
Yeah, so actually this is
This component part, sir, and that one more part I completely don't understand. Where they say like any n cross n matrix is connected, path connected, or anything like that. Can you do one question on that also?
okay, that will see. Okay, yeah, like matrix in MNR that is connected, that is because simply in MNR you can think of as like r power n square, that is just euclidean space. So any line, the usual line in r n square will give you a path in MNR also. So MNR is not an issue, but in like path connectivity of this SON or SLN, these are like these are some like particular thing that where you can get the like GLNR. Again, we just have seen in previous class that GLNR is not connected. So it actually has two component. One is like those determinant which has those matrices which has positive determinant, and those which has negative determinant, and they are actually connected. So you have to, if you are given two positive determinant matrices, you can actually get a path that connects one matrix to the other matrix through again positive determinants, let's say. So that is
when we say
yes
path between two matrix, it means some linear transformation.
No linear transformation, it is just mean a like you have gamma from close 0 1 to the your space, let's say GL n plus. So plus means the positive determinant part, GLNR. So here for each point you have a positive determinant matrix. So for example this is a like let's say you have diagonal matrices, let's say this thing. So one hand you have identity matrix, okay, 0, and you want to add this to a diagonal matrix, let's say A1 through AN. This is also diagonal matrix. So here the again all of the ANs, assume these AIs are positive, okay, greater than 0. Then like can you give me a matrix like this gamma such that this matrix connects to this matrix? So gamma at 0, this is gamma 0, and this is gamma 1. So in between matrix, can you think of something? Like it is just in the case, so what you define at gamma t, you can just take the linear combination
in a diagonal matrix, but on the diagonal I will have number like 1 plus I think t times a minus 1.
Yes.
A1 minus 1.
Yeah, so t plus 1 minus t into a1, then all the thing t plus 1 minus t an. Now like for the diagonal you have like for the part connectivity, again you can so that if you can connect every matrix to the identity matrix, then that is also path connected, right? Because the path component for that contains identity, that contains all other matrices, because you have connected all other matrices to identity. So that will give you this is path connected. Now how do you get a diagonal matrix from from a given matrix? So if your space the matrix you started with, if that is diagonalizable, then you will definitely get any matrix as p d p inverse, right? So you just take this path and take the p and p inverse. So at the one end you will get p inverse identity in between, so that is identity. On the other hand you get the required matrix. So that's the in general idea, like for symmetric matrices or this orthogonal matrices, they always are diagonalizable, right? So for any let's say belongs to SON, so you will get a matrix P, invertible matrix, such that P inverse equal to diagonal. So in particular A equal to P d P inverse, or P inverse dP. Then for how to connect this D and identity. So now if you can get a diagonal matrix that connects this to D, then that will also guarantee that how to connect this identity to this A. So definitely, so your determinant is positive will give you like the quantity A1 through AN. They are need not be all positive, but the even number of them can be negative also. So there you have to take a separate path, so that does not falls in something the negativity of them are still maintained, so that will not falls inside this. So this kind of in general idea to show the connectivity of those things. And the component thing is not also that hard. So suppose you start with a space X, then you if it is connected, then that cannot be written as disjoint union of two of its subset A and P. Both of them both are open and closed. A, B and non-empty also. So if you have only one component, then you can it is connected, that means it has only one component. And otherwise, if X is disconnected, then you can write this A disjoint union B, right? And this is again, now for A you can again consider this thing, so whether A is connected. So here only we are saying that A is either both open or both closed. But this A, for A with subspace topology, again you can consider whether this is connected or not. If this is connected, then you say this A and B are the two components of this. Else you consider again A as some A1 disjoint union A2, and keep going this. So after after certain number of steps, you will get X as some A1 union of this AI, let's say I, and some disjoint union of BI, BJ. Okay. So where the step this step stops, there will get each of these AIs are are connected, and you cannot go further. So those are the kind of maximal possible connected set. So below them, if you you cannot write as disjoint union of these things. So this might that's what the this problem is basically. So it seems that this X, whenever you have this collection of this AI and BJ, then they are component, and by the connectivity thing, this is actually all of these AI BJ are open or connected, open or closed. So in particular, if you take all of them as open, then this forms a open cover for X. So it has like finite subcover of that. But in general, it is not actually, in general these sets are not, need not be always open. So like that's the problem, where you, like if you have only two disjoint thing, then it is open as well as closed, because the complement of one is the other. But in general, actually it is not true, because the union of the one, like complement of the one, it need not be the, like obviously the complement of one is union of the others, but others is union of again maybe closed sets. So the openness of that thing is like you can't guarantee in general. So if you can say that the components of them are all open, then from the compactness you can say the components cannot be infinite, because if you have infinite components, then they are disjoint union of the components, and that cannot have a finite subcover, because if anything you miss, then some points of X will be also missed there. So in space where you can say the components are actually open, then you can actually say there are only finitely many components. But I'm saying in general, actually in any compact subset in a metric space, the components need not be open. So that's the like hint for this one. So can you, like, do you have seen any example where the compacts okay, so that you probably haven't like noticed there, but you have seen some example of spaces where the set is compact, and like compact you may not have seen, but that is closed and bounded, but actually that cannot have finitely many components. So you have seen such example in R only. Can you think of, so in R like components means yes,
1 by n and 0.
1 by n 0, that is closed bounded, so that is compact. So and it cannot have finitely many components. Sure. So it is closed bounded, sure. This is like, this is basically yes. So this is like discrete. So you that space cannot have finitely many components, because each of the point actually is a connected subset there only. Yeah, so that is an example. Okay, so now let's a equal to 1 by n union 0 with the usual like subspace topology of R. Sorry, so this is not discrete actually. So due to the point 0, because if you take any neighborhood of this thing, that will like include some points from this side, so you cannot get any neighborhood around 0 which contains only this 0. So sorry, this is not discrete, sure. So with, but the components of this also are not finite. Then is closed and bounded. This basically contained in again 0 1. So this implies is compact, but A has infinite components, as like A is disjoint union of these ANs. So much. Okay, it's a better way of saying that. Okay, so A is basically disjoint union of this n belongs to n 1 by n, and okay, am I missing anything? So any open cover, so this actually has okay, compact thing is fine. By components again, yeah, so okay, fine. So these are like union 0 and like for any n and m not equal, 1 by n and 1 by m, you cannot join them by any path, or they are just disjoint union. They are like open also, open as well as closed. So are the components of A. So these sets only, this 1 by n, they only has like infinite components of A. So even we forget about 0, for 0 also this is also only one component. Okay, so the only singleton sets are component, but okay, so this has infinite components. Okay, yes, anything?
That 0 is a limit point of A.
Yes, sure.
Then every neighborhood of 0 contains an infinitely many points of A. So the component 1 by n and 0, that is 1 by n contained in that. So it is not a
No, like component, again component mean that you cannot like, okay, so you are saying like 0 is not a component or something like that.
If we take a 0 is also a component, then 1 by n cannot be maximal.
No, like 1 by n is connected, or okay, so let's say okay, that's like points here are of the form 1 by n, and like anything connected sets in R, they are some interval, right? Any connected set in R, they are some interval, but in this case in the set A you don't have any interval. that is not discrete here. So if the set were discrete, that is like already have, like if you just delete 0, this set is clearly discrete. Now this set is like, this is union of this and this, but 0 is not involved here anyway. So like anything connected, if you say that 0 union something is connected, but that cannot be connected, because that you can write as disjoint union of that thing. And here each of these n are like each of these 1 by n's are like are open as well as closed also. So each of these 1 by n are like one component. So at least n many like natural number oath of component A has, and 0 cannot lie in any of those. Like, is this clear? So like this set clearly has like infinite components. Like,
Yes,
like the connected, the component means it has to be connected in that topology, but in R the connected subsets are only interval, and there is no interval content in A. So this has in like 1 by n, each of singleton 1 by n is a component only. So another like interesting example you can also like other one that you can think of, like Cantor set. Like similar kind of example. So this Cantor set also, you like if you recall, that is like closed and bounded, because Cantor set C constructed out of the like deleting the middle 1/3 like sub interval from the 0 1 in each step. So that is actually intersection of Cn's, n equal to starting with 0 to infinity. C0 is close 0 1, and C1 is like delete the 1/3 to 2/3 sub interval from this one. So it is 0 to 1/3 union 2/3 to 1, and keep the same process for Cn's. So Cn is obtained from Cn minus 1 by deleting middle third of each of its intervals. So each Cn of is like union countable finite union of closed interval, so they are closed. So each Cn is closed, and intersection of closed sets are closed. So C is closed, and it is already contained in closed 0 1. So this is also bounded, so that means it is compact. And the same like similar kind of argument also tells you that this has infinite components. The same thing. So this set is also not discrete, but like if you take any 2 points x and y from C, so C is compact, and if you pick, let's say, x not equal to y in C, then you actually don't have any interval that contains x and y, because again the same thing, the connected set will be in R. So this is in everything happening in subspace topology of R. So xy cannot be contained in one single interval. So because like you consider this mod x minus y, this is greater than 0, and see that this Cn length of this interval is 1. For this one, each of its sub interval has length 1/3. For the C2, you have length of each of its sub interval as 1/3 square, and so on. So each Cn has subinterval of length C2 1 by 3 power n. Okay, so you can definitely get a for any positive number, so you will get a natural number n such that this 1 by 3 power n is like it is strictly decreasing and converges to 0. So there exists a n such that 1 by 3 power n is less than mod of x minus y. Now this x minus y cannot lie in any of, because Cn has all its subinterval has length 1 by 3 power n, and the distance between x and y is strictly bigger than 3 power n. So this implies xy does not belongs to any of the subinterval of any one subinterval of Cn. So okay, so try it that way. X comma y does not lie in one single subinterval interval of Cn. In particular, all like this is also nested sequence. So C1 is contained in C0. So if it is not contained in Cn, so all the higher n also is not contained in any single subinterval. So because you are deleting more, like dividing into more parts and parts, so this implies that for any x and y not equal, they cannot lie in like any one subinterval, like one connected set. So the components of this set, Cantor set, are also singleton. So this implies xy does not lie in a component. That means the component are singleton. Okay. Okay, so that I'm not writing, and hence it has like C is actually the Cantor set is uncountable. That also you have seen previously. So there are actually uncountable many components, although the set is compact. Okay, because here you have like countable components, but in this case actually you have uncountable many components. Okay, so is this clear totally? Okay.
Yes.
Okay, so
Then in topological spaces, the components are always open.
no. In general, that's the problem. If the components were like in any topological space, or even in matrix space, if the like components are open or closed, then like closed you can say, but if it were open, then you definitely would get the finitely many components. But in this case actually they are not open, they are closed, like they may be closed,
Yes.
but need not be open. Yeah. Okay, so like okay, just you asked, so that's why. So in if you have two components, then it is actually true, right? Like if you have x equal to a union b, so a b both are closed means that a b are also open, because if they are disjoint, then the a complement is b. Now a complement is b means a complement, so suppose a b both are closed, so a complement is saying that also closed, so that means a is also open. So if you have two things, then these two are actually both open as well as closed. but the components thing is not necessarily this A B are the only components, so A and B may not be both connected. So in the components thing you may have like countable or uncountable many disjoint union. So as in this case it is disjoint union of countable many thing, in this case actually uncountable many of that thing, and each of them are actually component. Individually they are not like if you write as just union of disjoint union of two set, they are not okay, they are both open closed, but as a components if you write, then as a singleton set or in other set, so they are not necessarily open. Okay, so let's go to the next one. So if Y is compact, then just like related to this one, we have seen also like the projection map or quotient map. Moreover, they are open map, but they not necessarily are closed map. So in a like particular case, if your space Y is compact, then the projection onto the other component, like other set X, is actually a closed map. Okay, so if you just recall it, we in art 2 we have seen that if you like consider the projection onto the first coordinate to R, this pi 1, then this is not closed, because the like this xy equal to 1, this subset, this is being inverse image of a in the like this is a continuous map and inverse image of like xy. If you consider f of xy equal to xy minus 1, then f inverse 0 is actually this set. This set is f inverse 0. So as this is a like continuous function, so 0 is a closed set in R, so inverse image of a closed set is closed, so this set is closed. But the projection under this one, so if A is this, then pi 1 of A is actually R minus 0, right? So this is not closed because 0 is not a limit, like 0 is a limit point of this set but does not belongs to this set. So in general, because R is not compact, so we can say that okay, this is a instance that is happening in this case. But if we would have started with some compact set, let's say close 0 1, then the projection actually will be closed. Just if you do the same thing and cut out at like finite y thing, then actually we'll get a closed set. Okay, so this thing is saying that if you have compact set one hand, then you will actually get this closed set. So we need to prove, if you started with a closed set, let's say a subset of x cross y, let to be a closed set. To prove pi 1 of A is closed in X. So to prove this one is closed, we actually will prove that this complements of this thing is open. Okay, so prove pi 1a complement is open. So to show this is open, again we have to prove that each point of this thing is an interior point. That means if I pick anything from this set, I'll get a neighbor open set that contains x and lies inside this set. So let x belongs to pi 1 a complement, that is x does not belongs to pi 1 of a, but x does not belongs to pi 1 of a, that means pi 1 inverse of x, which is just the strip x cross whole of y. This is not actually not contained in F, that means it is contained outside of F, that means it is contained in, oh sorry, what I'm saying, this is A complement. Okay, so this is totally contained in A complement. A is closed, so A complement is open. Now can you say something using the compactness of y? You have seen this kind of thing. So this is an open subset in x cross y. Y is compact and it contains the strip x cross y. So can you recall something and say some, like give some neighborhood of x?
Tube's lemma.
Yeah, exactly. So using the tube lemma, you actually know that whenever you have such situation, a complement like some set A is open in x cross y and that contains a whole strip, then there is actually thick strip. So this is only one x cross y, so there is actually a neighborhood of x, ux. So ux cross y will be also contained in a complement. So that is again comes from the compactness of y. So there exists open ux in x such that x cross y in subset of this ux cross y, and that is totally contained in a complement as y is okay by tube lemma. Tube lemma or Wallen's theorem, whatever you say, tube lemma. As y is compact. So this is lies inside a complement. So the claim is actually x belongs to ux contained in actually this pi 1 a whole complement. So let's pick any y, let's say, suppose not like it is enough to show that any set like ux contained inside pi 1 a whole complement, that means enough to show ux intersection with this pi 1 a is empty. Like if this happens, then we like show that, like to conclude this one, it is enough to show that it does not intersect outside of this a1a, then it has to have content inside this complement, right? But if not, then y belongs to, let's say, ux intersection pi 1a, and this implies y equal to some, okay, maybe y is a bit misleading, it seems a points of y, but it is not, it is some, let's say x naught. Okay, x naught equal to this pi 1, because it is belongs to pi 1 of a, so it must be pi 1 of some x0 comma A, right, and okay, also lies inside ux, and x0 belongs to ux. For some a belongs to, okay, I'm missing something, pi 1 of a, okay, pi 1 of a, that means some x naught comma, okay, some a belongs to y, okay, that I should write y, okay. But can this happen? Like x naught lies inside ux, so x naught comma y actually will this implies actually x naught comma y, this is belongs to a and intersection with okay, so I basically want to show that this ux cross y is totally contained in a complement. So ux like x naught comma y, this is actually belongs to a intersection ux cross y, right? Because x naught belongs to ux, so x naught comma y also belongs to ux cross y, as well as this is also belongs to a, because x naught belongs to pi 1 of a, so as it is image of this pi 1 of x naught y, so this also belongs to a, right? But this cannot happen, right? Because ux, which is a contradiction, as ux cross y is totally contained inside a complement, so this implies that there in ux cross y intersection a is phi, right? So as ux cross y is contained in a complement, so this completes that this intersection is also empty, hence ux contained in that thing. And we started with any arbitrary x, we showed it that there is an open set that contains x and lies completely inside pi 1 of a, hence x is an interior point, and thus this pi 1a complement is open, hence pi 1a is closed. Fine. Okay, so any doubt, or should we proceed?
No, sir.
Okay, so let's proceed then. So suppose in this thing again, like if you have a space where like which is a compact metric space, for such spaces if, like there is a like particular characterization of a continuous map. So if is continuous from x to y, so x can be any arbitrary topological space and y is in particular compact metric space, then checking this f is continuous is enough to check this set in x cross y, which is called graph of f, consists of points x comma fx for x belongs to x. So this set is closed whether this set is closed or not in x cross y, right? So let's do the forward part. So suppose f x to y is, suppose x to y is continuous. So we need to prove this graph of ape is closed. So again we'll show the complement of this thing actually open. So we'll show this graph of ape complement is open in x cross y. So again, to show something is open, again we start with some point from here. So let x comma y belongs to complement, but this consists of all points x comma fx. So clearly, as I'm saying, this x comma y does not belongs to graph of f. So we must have y not equal to fx, right? Now actually we need the metric space of this thing y, because these both are happening in y and y is metric space. So we actually can get like balls around y and fx which are disjoint from one another. So that is like particular specialty of metric space. So in some other spaces also that is hold, and whenever you actually, that is called Hausdorff property. Whenever you have in a topological space, if you can separate two distinct point by open set, then that is called Hausdorff space. So all metric spaces are Hausdorff. So actually the Hausdorff space, like Hausdorffness of this topological space y is enough, like not full generality of matrix space is needed here. But okay, so in our case we will just do for matrix space. So consider br by 3, or let's say br of y, and so br means the ball of radius r around y, and similarly here around fx, or r equal to 1/3 of distance between y and fx. So as y and fx not equal, so this clearly greater than 0, right? So these balls are valid open ball around y and fx, and clearly then br y intersection with br fx, they are pi, right? Because they are already like 1/3 distance apart ball, so they cannot intersect. Any point of this ball cannot intersect any point of this, right? So this is phi. So like now can you say what is like possible? Hello? So can you say like possible choice of your this neighborhood around x comma y? Can you guess something? Any guesses? Like you get two separate thing around y and fx, okay?
Since y is compact, we need to make an open cover of y.
Open cover, but
Y is compact.
yes, sure, but yes, sure, that you can, but like first can you use continuity? So both these things are happening, like this is an open set, this is an open set.
Yes, yes. Inverse image of open is open. So F inverse of BRY.
F inverse of BRY, and what you precisely will take this thing, like I want some neighborhood around x comma y, right? So BRY is actually a neighborhood around y. So what is a possible neighborhood around x?
Then that will be F inverse of B
Yeah,
or of
so
F
F
of
inverse
X.
of that thing will be this one. So note that x comma y, this is actually belongs like F inverse of BR fx. So this is an open ball around fx and f is continuous, so inverse image of open set is open, and this cross you consider BRY. So this is so okay, open in x cross y. As if is continuous. Right, so we get a neighborhood around x comma y. Now we actually
So this complement. Okay, this graph is a subspace of x cross y. So when I take its complement, it's also a subspace of x cross y. But now the second element, it cannot be it cannot be in f of x, but
Yes.
it can be in y. Okay.
Yeah, sure.
I thought the other point is also from this this x space.
Yeah,
From
so
y.
yeah, that is not true, like yes. So like this is particularly also some x comma y prime can be there, where y prime is some point like some f x prime. So that point lies here in the graph, but like y prime cannot be exactly f of x. So those points are also allowed, like this y can be lies in the image of f, but the immediate point of like in the first coordinate which point you are considering, that point cannot be image, the y cannot be image of that prime, that point. Yeah, so complement means that only. Yeah, so now actually my claim is that this set, let's say u, this set actually will be contained in the complement. So claim this u is contained in graph CF. Okay, so here actually we for this forward part actually the compactness is not needed, but the house drop thing or just the metric space thing is good enough to conclude. Okay, so now this thing, so you start with any point u, let's say from okay, again we may so that u intersection graph f is empty, then we'll be done, right? U intersection graph f is empty. Okay, so if not, let okay, both are like there are some, okay, they are subset of x cross y, so let's take x prime comma y prime belongs to u intersection graph of f. Okay, and once it is graph of so x prime y prime belongs to graph of f means that y prime is f of x prime. So this implies y prime equal to fx prime. And okay, so just maybe this implies x prime y prime equal to x prime fx prime, and that is belongs to u. But what is u? U is the cross of this thing, right? So it means that fx prime belongs to bry, right? But okay, I want to use this one, like bry and brfx, they are empty, but in this case actually I'm getting that they have some intersection, right? Because x belongs to this set, that means fx belongs to that set. Yeah, so this implies belongs to u means x prime belongs to f inverse of this thing. This means if x prime belongs to brfx, and as well as fx prime also belongs to bry, so this belongs to bry also. Clear? So here this x prime y prime belongs to u intersection graph of f. That means is y prime is f of x prime due to the graph thing. And now this x prime comma fx prime belongs to u, but u is the cross of this thing, f inverse of brfx and bry. That means x prime belongs to f inverse of brfx. That means f of x prime is belongs to brfx. And also from the second thing you know that fx prime belongs to bry. That means fx prime belongs to brfx intersection bry, and it is empty by our choice, so which is a contradiction. So this implies u intersection graph of f is empty. So once this is empty, this means this is content. Hence we get a open set that contains x comma y, an arbitrary point of the complement of graph of f, and that totally contained inside that set. So this implies graph of f is open. Graph of f complement is open. So that means graph of f is closed. So here we didn't use anything about the compactness, only the Hausdorffness mainly, that you can actually separate 2 points in the codomain. That is enough to guarantee that graph of f is closed. Now for the converse part, actually we will need the compactness. Okay, so converse, so graph of f is closed in x cross y. Now how do you proceed, like to show f is continuous? We will show that inverse image of any open set is open. To show f is continuous, will show f inverse of u is like, okay, not f inverse u is open, so that you can show, but we'll actually show point wise maybe. Yeah, we'll show point wise. We'll show for any x belongs to So basically if you pick any point y belongs to capital Y and an open set, let's say belongs to V, it's an open subset of Y, then there exists a open subset U in Y belongs to Y and open V subset of Y. Okay, open V with Y belongs to V, content inside Y, there exists open U in, okay, for not for any Y, okay, sorry, for any fx, yeah, I want any Y fx, there exists open U in X such that X belongs to U with f of U contained inside V. Okay, so like this is showing that for like f is continuous at the point X belongs to X. So for each point this X is an arbitrary point of X. So for a particular X, I choose like I took fx and a neighborhood around fx V in Y. Then if I can show that there exists an open set U in X containing the small x such that if U is contained in V, then that also guarantee that f is continuous at the point X, hence it is continuous at all point of X. So just start with for fx belongs to V subset of Y and V is open Y and V is open. So like V complement is closed in Y. Like once you know that V complement is closed in Y, so you can take X cross V complement, right? So then X cross V complement is closed in, okay, this is closed in X cross Y. And you also know this graph of f is also closed in X cross Y, right? Graph of f. So if I consider the intersection, X cross V complement is also closed X cross Y as is closed. Okay, now so I want to get something, some open set U, right, around this point X. So this X comma fx, and like that does not belongs to this set. So this thing, if I take like this is closed, so if I consider the projection onto the first coordinate X, then this gamma f intersection X cross this thing is also closed, because we just have proved in the previous thing the projection, whenever y is compact, the projection onto the first one x is closed map. So pi 1 is closed in x. Okay, once this is closed, you can consider the complement, because here the point like x comma fx does not belongs to here, because fx belongs to v, so fx does not belongs to this. So you are again complementing that set. So let's take u equal to pi 1 graph f intersection x cross v complement and this whole complement is open in x. Now claim is that this, now what is this set? If you just see, this is consist of all points. So this consists of all x belongs to x, such that this the points of this intersection is of the form x comma fx, right? And fx does not belongs to okay, this x may be misleading. Okay, I should change with something, let's say let x prime. Okay, then this x prime comma fx prime, that is a point of in this intersection, because that comes from the graph of this f, and that fx prime does not belongs to v complement, right? And so this is complement of fx prime, such that fx prime does not belongs to v, right? That's the like typical element, x comma fx prime, but fx prime cannot be anything cannot be any arbitrary thing, that should come from v complement, but v complement means it does not belongs to v, and complement of this set. But this is precisely what this is, f inverse of v complement and the whole complement of that thing, because that means x prime belongs to f inverse v complement, right? So if I just write, instead of not belongs to, just write fx prime belongs to v complement, that means x prime belongs to f inverse v complement. That means this set is totally f inverse v complement, and outside there is complement. But f inverse of any complement is complement of the inverse, so this is nothing but f inverse of v, because it is f inverse v whole complement and then complement, so that is just f inverse of v. And v is open, so f inverse v is again open from that thing also, but in this setting you are getting in this way. Now this u is actually, you are getting exactly, this implies I want to claim that fu is contained inside v. So f of u is f of f inverse v, right? F of f inverse v, but f of f inverse is contained in v itself, right? So you are going there and then coming back here. So in v you may have something more element which is not image of anything, so it is actually subset of v, right? Unless this f is onto, so we in general it is f of f inverse v is a subset of v. So this completes that u is an open subset and containing obviously x, and x belongs to u. Why? Because fx belongs to v, so fx belongs to b, so sorry, I'm missing something. Yeah, so x belongs to u as fx belongs to b. That means f inverse x belongs to f inverse b as fx belongs to b, so x belongs to f inverse b and f inverse b is u. So this completes the continuity part. Clear? So here we are like crucially use the compactness. So metric thing we did we use anywhere? Yeah, in this part, the metric part we didn't use, we only used the compactness. Clear? Okay, so then let's go to the next one. So here again, like if you have like one of these thing you probably have seen or related to the assignment, that if you have a uh, a closed set and compact set, then you can actually closed set or compact set, or just compact set at a single point, that you can actually separate by if the point does not belongs to the compact set, then you can actually separate those two by open neighborhood of the points and the compact set. So in this is in general, right? If you have two compact subset in a matrix space which are disjoint, then you can actually construct open set u and v that contains a b and still u v are disjoint. Okay, so any idea for this one? The ingredients, we actually have almost all of the ingredients we have actually. Like in general in R, if you think of this thing, so compact set are closed and bounded. So in particular, let me take as like interval, closed finite interval. So they are like compact set, and disjoint means then there is some like gap in between, so some gap there. So you definitely can consider like something, consider the distance between these two set and consider half distance and take the ball around this thing, and that will be the required neighborhood of this thing. So similar idea will be similarly applicable here also. So can someone give the choice of these open sets? Like these are happening in matrix spaces, so anything, any idea? Okay, so like two things, a b are compact subsets of xd. So whenever you have two sets, the product of them is also compact. So a cross b is compact. Yes.
Using every element of A, we can construct a wall around A, which is disjoint from B. Like that, we can form an open cover of A.
Yes,
With
right.
the same argument, we can form an open cover of B.
Yes.
But being compact, we'll get finite cover.
Yes.
That will be our U and B.
Yeah, so that is definitely a way. So you can actually like for each x comma, as these are disjoint compact sets, so you can take a comma b, there are two disjoint points in x. So as this is happening in metric space, so you can actually get a like just fix a and consider all b belongs to b, So then you will definitely get like this UA, let's say, okay, fix A, then UA B I'm saying, but this is bad notation. Okay, cross some VB for each point B belongs to capital B, and these two are again disjoint open set in X. Then you can actually cover this whole of B by this set VB, but B is compact, so you will have a finite collection of this VB, and now you consider like intersection of those corresponding U AB, and that is finite intersection of open set, so that is again open and also contains A because all of the set contains A. Now you you have for each point A, you will get a neighborhood of such A cross this B, right? Now you vary this A and you will get again a cover of A, and again you consider the corresponding finite subcover of that. Then that finite subcover cross this thing will give you a cover like total two open set which are also contains A and B both, and they are clearly by disjoint. They are disjoint because at each step we are considering disjoint or open sets. So that is a definitely a way. So like a more like clear proof using the things which we have seen already. So I'm going to use that thing. So AB is compact as AB both are compact. So product of two compact set are compact. Okay, so now you can consider the distance function. So D from A cross B to R. Okay, and this is a continuous map from a compact set to R. So this has a like if you consider the so D is, so it sends AB to distance of AB, the metric, the given metric. Okay, so basically the metric in this case given, that's why I'm actually using this one. Otherwise the general proof, actually the Hausdorff thing are like mostly important in that case. So but in this case I'm as my space is metric space, so I'm using the distance thing. So it's a continuous map, so this you have seen in like one of the theorem, not hard to check that image of this thing is compact here. So if you consider the so compact means that in particular closed and bounded, so the supremum and infimum of the image set is like is attained by some points here, right? So this implies, so in particular I need in this case infimum of D A cross B, this set belongs to R is achieved, that is let's say infimum is R equal to infimum of this D of A cross B, and that is achieved by some D of A1 B1 for some A1 B1 belongs to A cross B. Okay, this infimum is achieved, and this cannot be 0. because this is achieved, so D of a1 b1 as a1 b1 are distinct, like not equal, so this cannot be 0. This implies R is strictly greater than 0 as a1 not equal to b1 because they are disjoint. So consider the open ball, consider U equal to the union of all the ball of radius like R by 2, let's say BR by 2 A for A belongs to A, and V equal to union of all again R by 2 radius ball around each point of these points of B. Then UV clearly U and V are open and A contained inside A, because A is contained in each ball, so A is contained inside U, B is contained inside V. So only the disjoint part is left, but disjoint part is also clear because like also U intersection V equal to phi, because the like least distance between any two points of A and B, that is this R, and I am taking already half distance from that, so anything like any ball around any point of A and B that cannot intersect each other, because that will mean that there exists a ball of radius R by 2 which has points some points from like A and B, which will like contradict this is the least distance. Okay, so just if I write, if not, there exists some, let's say x belongs to BR by 2 A intersection BR by 2 B. That means for some AB belongs to A cross B. So this implies if I consider D of AB by triangle inequality, D of AX plus D of XB, but both is as X belongs to this thing, so this is less than R by 2 and this is also less than R by 2, so this is less than R. So DAB, I get 2 points A and B from AB whose distance is less than R, and R is the infimum of all possible such distance, so which is a contradiction. So U intersection V is definitely phi. Okay, so this is like a proof that involving D, and otherwise if you have just the house drop thing, then you can proceed by the previous argument as suggested. Okay, so next we have this one, just using the previous thing and this compactness. Like in one of the theorem you have seen in side note that if you have a compact matrix space and a collection of closed set, nested closed set, then the intersection of all those closed sets are actually non-empty. So in this case I am saying that if you have like this compact matrix space, then this collection is not, intersection is not only non-empty, that is actually connected. So the intersection cannot be contained like two distinct point, so that is not connected, so that is actually connected. So the idea, so already I'm running out of time, so I'm giving a brief idea. So to the contrary, suppose A is union of two like not connected, so it has some disconnection or separation. So let's say A equal to some U disjoint union V. U, V are both, let's say, closed. Okay, then they are closed subset of U, V are closed. So they are closed subset of in a complete matrix space. so they are also compact, right? This is also UVR compact. Once you have compact and their UVR disjoint, like UVR already disjoint, so using the previous thing I can get an open set around U and P in X such that okay, the notation may be okay, U is contained inside some U prime, B is contained inside B prime, U prime B prime open. Now you like see this one, A1 minus U1 union U prime union B prime. So U prime union B prime, that is a like open set in X, and A1 all those are closed sets. So this is basically A1 intersection this complement. If I just write the minus thing, so this is still will satisfy this thing, intersection U prime union B prime complement and so on. So this is U prime like U prime union B prime whole complement, that is still a closed set. So intersection of two closed sets. So this is still a like it's still a collection of closed sets in X, and again this is happening in XD. So this implies the intersection of this all this AN intersection U prime union B prime whole complement, this is non-empty. But what is this? This is just intersection of ANs, which is A, and that intersected with U prime intersection B prime whole complement. That means equal to A minus U prime intersection B prime. But this UV already contained in this set. This means A is contained inside U prime union B prime. That means if I delete A minus U prime B prime, that is empty. But in this thing you are getting that is non-empty. So which is a contradiction. So you can't have a separation for A. So A has to have connected. Okay. So next, suppose we have a continuous map from a compact subset X to a metric space YD. So again this thing is the full generality of matrix space is not needed, only the Hausdorff thing is good enough. Like again then that map will be closed, which in general actually will imply that if you have a continuous continuous bijection from a compact space to a Hausdorff space, then that is a homeomorphism, because like if you are showing that is a closed map, so the inverse is actually continuous, hence that implies the inverse is also continuous. So for that, like a general thing that if you have one on two you don't have, but you have a compact space to Hausdorff space, you have map, then the map is actually closed. So it is again easy. So you start with a closed set in X, then A is closed in a compact set, so this is compact, and if is continuous, that means if A is compact, continuous image of a compact set, so this is compact, but a compact set in a metric space is closed, so hence this is closed. So the compact space actually in Hausdorff space in general, that is closed. So as you know, in metric space it is already true. So FA is a subset in a compact space in metric space, so hence it is closed. So that's about this thing. And last one, that countability is like you consider R with cofinite topology, then whether that topology is first countable, second countable, or whether that is separable. So first countable means that whether at each point of R you have a countable neighborhood base. Again, neighborhood base, recall that neighborhood base is like if you have any neighborhood base is such a collection that neighborhood you can write as union of your that collection. So that is called a neighborhood base. Just like base, you have any open set you can write as union of those set, and in neighborhood base you actually write the neighborhood only. So any guesses about this first countability or second countability of this topology? Okay, so just check that these actually are okay. One like thing that if you have a like second countable space, then that is automatically a first countable, because you just consider those basis element which contains your that point x. So second countability always implies the first countability. So if it is not first countable, then it also cannot be second countable, right? So if you start with just the first countability, you will actually see that this cannot be first countable. In general, if you have any uncountable set with cofinite topology, then that cannot be first countable. Just prove by contradiction. Okay, you start with any like countable neighborhood base around any point, and then using the cofinite topology thing, that if you consider the union of all those all those complements of those neighborhood base, that will be countable, right? Because each of the complement is finite, so union of those finite set will be countable union of those finite set will be countable. But R is uncountable, so there are infinitely many points outside of that union. So you pick any one point of that thing and take the complement of that thing. So that will be a neighborhood for your point starting point x, but that you cannot write as union of your collection, because that gives you countable many thing only, but your chosen interval is already does not contain x. So okay, so that is just a like proof by contradiction that it cannot have a countable base. So okay, that are with cofinite is not first countable. Even if you just replace this cofinite by co-countable, the argument will still remain same. So instead of the countable union of finite set, you will get countable union of countable set, but that is still countable. So if the space x is uncountable, so the argument will still remain same. It's not countable, hence it is not also not second countable. But like it is separable. Separable means there exists some countable dense subset. In cofinite topology, actually every infinite set, not necessarily every infinite set is dense, because if you like consider any neighborhood, any open set, like dense subset means any open set should intersect that set. But if you start with any infinite set, then the complement of any open set is finite, so and your starting set is infinite, so though that set cannot be contained in fully in the any complement of an open set, so it must intersect the every open set. So every infinite set in R is dense in this topology. So in particular you can take Q, which is infinite countable. So even n you can take natural number set, that is also infinite, so that is also in this case dense. Or Q is also countable, so n is countable, so whatever you can take, Q, n, Z, whatever, all of them are countable dense set. So this implies R is separable, right? Hence this with, so this argument will not hold in countable topology, but this argument will still hold. So in this case actually the R with cofinite topology is separable. Okay, so that's all I had to discuss. So anything else? Anyone have any question?
Sir, on this NPTEL portal, like we have to submit the 8th assignment,
Yes.
subjective.
Huh.
They have told us to upload 3 separate files, 8.1, 8.2, 8.3, like always.
Huh.
But this time, when we add one file, there is only space to upload one file. So maximum of one file is allowed. We are not able to upload all the 3 files.
Actually, I don't know. Actually, in the I'm completely unaware of what is happening on the portal or anything like these things. I'm doing separately. Yes.
Okay, whom to connect, because I put one mail on that portal also where
Yes.
we discuss our problem.
Nobody
replied from there also. Tomorrow is the last date for the assignment.
I also don't know who is the handling all this. You may directly connect to the NPTEL. There is some mail for NPTEL total help desk or something there is, right? I'm actually not aware of these things, so I can't help in this regard. So you might write some mail to the administrator of this NPTEL, where you are getting this mail regarding all this tutorial session or anything.
Okay, sir.
That you can do. Yeah. Okay, so if there is no other question, then let's stop here.